I'm going to try and print out the notes as much as I can. It's only 4 people. It's not that big a deal. But just to kind of give an introduction into what we're doing here in soil chemistry, I'd be remiss if we didn't go over the history and the purposes and the reasons for why we're here. There are always going to be several different definitions of soil. It all depends on who you talk to. You can talk to a soil physicist, a soil chemist, Dr. Branson, Mr. Livingston. Someone's going to have a different definition of it. But for the most part, solid air, water, microorganisms, plant roots, and other types of biota that basically work to grow plants, right? That's what we're here for. If we're trying to grow some sort of plant, a crop, whether it be a specialty crop, or whether it be corn, or whether it be using some sort of plant to remediate the environment. If you had taken my soils class, it would be the unconsolidated matter collective of basically the inorganic and the organic solids, organic matter, plant roots, a medium for growth. And so typical traditional soil chemistry, we looked at those abiotic factors and the things and how they transform those. So abiotic being water or pH or air, things of that nature, the not living things. So when we talk about the biota, we mean like microorganisms or macroorganisms, how ants or earthworms are creating channels that allow the air to move in. Typically look at the oxidation states of the elements, and so when we have air moving, we have oxygen, and that is going to change the oxidation state of that element. And when we have ions that have different and changes in oxidation states, that's going to affect not only adsorption to the soil colloid, but also the ability of a plant to be able to take that element or ion off of the soil colloid and use it in its plant material for growth. So there's a balance of how much oxygen we have in the system that is going to affect on whether or not it is NH4 plus or if it's NO3 negative and everything in between there. And so then today in modern soil chemistry, it's really about the interaction of both those abiotic and the biotic influences, because again, earthworms dig a channel that open up more pore space for oxygen or water, and that is going to affect the oxidation state of those elements and how the movement and diffusion in the soil solution. And so soil chemistry is really about this attraction of those ions to this negative surface or positive surface within soil. And so we have this soil solution solid phase interface where we're really looking at how the attraction is right there at that surface. Most of it's empirical. We cannot see most of it. Some work has been done with electron microscopes, and they can see all these different radioactivity elements and molecules, but for the most part, it's theoretical. And guess what? It's always changing. So they can never find the right answer. So soil chemistry actually has a very good job security because it's always changing, and we'll see that in just a minute. Sir Francis Bacon is the father of the scientific method. So we're going to form a hypothesis. We see something and we say, hey, you know what? I believe this is a thing. Let me test that theory. And I have a big problem with this because now I am a scientist, and so I'm constantly testing theories in my regular everyday life. This thing happens, and it's a cause of this or that. We'll remove this and see if it's a cause of that. And if it's not a cause, we'll add this back and see if that's the case. If neither one of them, well, then my hypothesis needs to be retested. So that is the test. We will either remove one thing or add one thing and see what the result is. Once we're done, we'll analyze that and say, oh, this is the trend in this system, that when we add this, X increases. When we add X, Y changes, either positive or negative. We're going to basically do a report and report the results of our findings. This either did or did not work. And then finally, we'll reobserve. I got a feeling that observe was probably first. And I just did that. I didn't set that up correctly. But we're going to observe this thing. We see this phenomenon that happens in whatever. We're currently looking at soil, but it can happen in anything. We're going to form a hypothesis and say, I believe that it is this causal. We're going to test that theory. We'll try a control, and then an intervention is what they call it. We will analyze the results and form a report, and we will go, well, that either did or didn't work. Maybe it's something else. Repeat the process. So, where is it? This is in the, got to be in the 15 or early 1600s. John Baptiste van Helmont did this willow tree experiment. And basically what he did is he air dried soil, weighed it, put it in a pot, had a willow tree, weighed the willow tree, put it in a pot, covered it so that the only thing that could enter was rainwater or regular irrigation. At the end of it, at the end of 5 years, the tree grew from 5 pounds to 169 pounds. Where did the growth come from? He only added water. Right? Because that's what plants do. They take up water and that's how they grow, right? So what he said was that water must be the thing that is driving this growth, because that's the only thing that he added to it. And he calculated all the water that he added as well that was added to the tree. And out of that 164 pounds, wood bark and roots arose out of water only. What he didn't know was that in the soil, all the nutrients that were necessary for the plant to grow, the 17 macro and micronutrients were in there, right? C. Hopkins Cafe, managed by my cousin Boccolini. All of those were in there. They were also in the rainwater. And something else that I noticed when I was making this was that he put an iron cover over this pot, right? Why would you, but I mean, that's all he really had. So whatever elements and impurities were in that iron also came in. He didn't know that. So this is like, so when Van Helmont did this experiment, it was like literally a decade after Francis Bacon had come up with the scientific method. So he was still just like, holy crap, like I added, like this is what happened, it was just the water. Didn't think about that there was iron, that there were nutrients in the soil. They just thought that it was dirt, that there was nothing else in there. They didn't know why plants grew. So kind of one of the beginning experiments to lead into or be a catalyst into what we now know as soil chemistry. Next, John Woodruff followed right after him and said, well, let's try this with different types of water. So he took a spearmint plant and this is the rain. He took some river water, sewage, and then sewage plus mold. And what he found was that the more impurities in the water, the greater the plant growth, right? So there's something else going on here now. So just regular rainwater, they didn't have a lot of carbon dioxide, there wasn't a lot of nitrogen emissions, like they didn't have the global warming and environmental change and all that stuff, the environmental pollution that we had. Mostly just methane from a bunch of cows. So the rainwater didn't have very many impurities in it. The river water did though, because that's where everything runs, right? So all the runoff and all the chemicals kind of go into river water. And then the sewage, and what he did is he took some garden mold. And so we now know that this mold is kind of like that mycorrhiza that helps improve nutrient uptake, and that is shown here. As we start getting into the more soil fertility part of it, Von Liebig piggybacked off of Springel's work and found that the mineral salts are responsible for the growth. So they started doing the research and found that from Van Helmont's experiment, that the nutrients in the soil actually were the reason why the plant grew. Von Liebig's law of the minimum, that crop yield is basically correlated to the minimum level of the most deficient nutrient, whether it be water, whether it be light. If the light does, you can have all this filled. We can have C. Hopkins Cafe, managed by my cousin Mokel Nina, maxed out. There she is, Aunt Alicia. We could have that all maxed out and have that all sufficient, but if we were to put it in the closet, the plant wouldn't grow, right? Because it doesn't have enough sunlight to make the photosynthesis to get the whole plant thing doing. So Von Liebig came up with this whole law of the minimum. The growth is limited until all factors and nutrients are adequate. So after Von Liebig came out, there were a whole bunch of people who just, there were haters everywhere. Like, just haters gonna hate. And they wanted to prove him wrong so bad that they set up an experiment station in England, Rothamsted, where they started doing soil fertility research. And then several different kind of findings came out from Rothamsted. And that's probably more of a soil fertility thing that we will go over. But in soil chemistry, we started getting this separation between the two sciences. It used to be soil fertility. Then finally some other people said, hey, wait a minute, there's some other stuff going on. Van Bremelin started talking about looking at clay minerals. Okay, and so by this time in the 1850s, we started having microscopes and you can start to see things a little bit better. And chemistry was getting to be a big thing. And now chemistry is kind of like that theoretical thing. We have to trust it, right? Because we can't see electrons. So Van Bremelin came in, developed this theory of adsorption. A couple of other people moved on, and when we discussed the diffuse double layer, that is going to be where Goya and Chapman come in and kind of separate everything out, and they go, we're going this way. There are now chemical properties that are governing the adsorption and release of these cations and anions, right? Everybody bored to death by now? Same stuff, right? I know we sit here and we go over the same stuff. It's like, Natris, you told us this in fertility, and we both got it in soils, and you're like, yes, I remember, dude. I remember some of those principles. So the soil environment is made up of all these things, different changes between the biosphere, the hydrosphere, the lithosphere, and the atmosphere. And it is this biogeochemical cycling that soil chemistry is really founded upon, because those are bio and geo and chemical. And we'll go over this in a couple more slides. How those things influence the chemicals and the energies among all of those. Why is that shaking so much? You have an earthquake? Is that shaking you all?
A little bit.
Yeah.
I think is somebody walking upstairs? That would make sense. Why not shake?
Could be. Unless they're doing some weird experiment up there with something. It doesn't matter. So there's these interactions that go in with all of this. And so this is where we start to come in with this abiotic, while being in the atmosphere and the hydrosphere between precipitation and evaporation. A little bit of the lithosphere, because that is where we get this, that's the geo part of it. That's the geology and how these soils break down into different mineral fractions. And then finally we have this biosphere, which now brings in that biotic portion of it, which is our macro and microfauna. So all of these things are all going on at the same time. And after I took soil chemistry, I went, so y'all really don't know, do you? There's really no answer. I found that they're basically they're just chasing rabbits. Now they have some concrete evidence of what the things are going on, and it kind of holds true and gives us the science that we know today. But in the end, I found was that, like, y'all really know, do you? They know some. But because these things change constantly, so if one change happens in the hydrosphere, it affects all the other ones. So if you were studying the biosphere, something happened in the hydrosphere, everything you just learned and did is now starting over at fresh, right? Because now we've added water. Water changes, boom. If something breaks down in the lithosphere is probably more concrete and consistent. They know that the geology happens exactly like this, and it's a very linear thing. It's static, it does not move very much. Rock weathering, groundwater recharge. Something happens in the biosphere where we get a change in elemental cycling, where we have nitrogen that now volatilizes into the atmosphere, changes the petosphere, now we have a soil water thing. So each time something changes in one of these spheres, you're basically starting over, right? That's what I come to learn out of soil chemistry. That's why I say that there's job security in soil chemistry, because all you have to do is change one little thing and it gives you a whole new area of research to go through. Just a couple of definitions just to kind of make sure that we're all talking about the same thing. Sometimes a soil chemical to me might be, when I think of chemicals, I'm thinking of nutrients or micronutrients, macronutrients. But there are plenty of other elements that exist in the earth and in the soil from the lithosphere, like those elements like arsenic, lead, tin, cadmium, chromium, aluminum. Some of those other elements, they do exist there. So those also affect each one of those nutrient cyclings and the other thing. And so it's like every time you dig into something, it changes. It's just like, oh my God, are we ever going to get to the answer? No surprise here that soil is the buffer of the changes. Like it's extensive. It has the ability to take on the responsibility of cleaning the environment, and it does very well at it. However, if we bypass the soil, then we have environmental problems. So think about rainfall through the soil profile recharging the aquifers, right? If it passes through the soil acts as a filter. Because the rainfall happens so quickly now, there's no opportunity for it to enter into the soil, and it runs off. So all the acid and all the pollutants that are in the rain are not in the soil anymore, they're in the stream. Kind of makes sense, right? So if you bypass the soil, so we can use soils as filters, remediation, things of that nature, and those, the pollutants or the chemical that is in the rain, the soil can then change that into something that the plants can use. So it's not only a filter, it also recycles these elements through the biogeochemical cycling. Oh. Okay. So the factors that are going to affect this are going to be how much of the element is there? How much ion is present? Do we have a lot of nitrogen? Do we have a lot of carbon? Do we have a lot of aluminum? Aluminum is going to affect acidity. So knowing the concentrations, that is our starting point. So we take a soil sample, send it off to the lab, They tell us what we have so that we can start our formula. If we were to write out a formula, right? We have this ion concentration, we send it off to the lab and they say, hey, you know what? You got a lot of hydrogen, you got a lot of aluminum, you need to add lime. Knowing the ion concentration allows us to figure out how much lime we need in order to have some change in the soil. That is at the very basic of what soil chemistry is. And that's not getting into all those, I've got some crazy calculus type equations where they're, have y'all ever seen the equations where they're like, if this is true, then we can do this, and then they come up with a completely different formula, and I'm like, how did you get from, why didn't you just start there? That's the type of stuff that's in the book. So if you're gonna be a soil chemist, to have that mind that can understand that flipping this and changing that in calculus, over there. That's not what we're doing here. So the degree of the ion interaction and release from the soil solid phase, cation exchange. So we can do these adsorption, desorption reactions, and they've already done most of these. You can find these online. But knowing how fast or slow this is going to release is going to help you figure out the change that you're going to need to incur. Here's the abiotic problem. Soil microbes are increasing or decreasing the rate based on some abiotic influence. Yeah, they got something serious going on up there. It ain't the sewing lab.
You can feel the floor move when you walk upstairs.
Oh, really?
Yeah, it's pretty sketchy.
Okay. Okay. So what do y'all think some of the things that are going to affect our soil microbial activity? There should be three right off the top. When do we expect microbial activity to be the greatest? Hot or cold? Hot. So temperature is going to be one that influences that. And would the soil microbial activity be more, would be greater in moist soil or dry? So water. And microbial activity in anaerobic or aerobic systems, depending on the microbe, right? Some microbes are anaerobic, some microbes are aerobic. So moisture or temperature, moisture, oxygen. Those three things are going to be part of this kind of, there's another little temp, moisture, oxygen. Those three things are what's going to influence the soil microbial activity. Once you change that, if we were to go back here, remember when we have one change, so now if we increase the temperature, we increase evaporation. If we increase the evaporation and the water moves out of the soil, what happens to the microbial activity? Moist or dry soil, do they prefer? Moist. So if we lose all our soil water, what happens to the microbial activity? It goes down. What happens to the reaction over here? It changes, right? So each time one of these things changes, we're changing a rate of microbial activity that is about this ion concentration and nutrient cycling. And then finally, plant uptake, which is really the ultimate goal, is we're trying to get these nutrients into the plant. The great thing about plants is there are 17, and some people might argue that there's like 20 essential nutrients that plants take up. Some people think that silica is, and if you're in turfgrass, that might be true. But plants also do take up some of those other arsenic, lead, selenium, chromium. They do have the ability to take those up through mass flow. Not necessarily diffusion, because the plants don't need that. But through mass flow that's in the water, as they suck all that water out to get into their plants so they can survive, now we've influenced the soil microbial activity because the water's not there. Temperature, we increase the temperature, we increase evapotranspiration by the plant, which affects the soil microbes, which affects it, and it just cascades over and over and over again. So, each one of those things to think about. Discrimination by plant roots, they're going to take up the things they need. Nitrogen, they're going to specifically seek out nitrogen. Phosphorus, potassium, calcium, magnesium, sulfur. Specifically those things. And when you remove those from the soil, now we have an imbalance in concentration. Start all over again. So for biogeochemical cycling, it's biochemical plus geochemical. It's the transfer between the chemicals and the energy, the biosphere, that oxygen and water is what's going to affect the biogeochemical cycling. So we cannot have weathering processes without air and water. And then also the available nutrients in the soil to be taken up by the plant. And so I guess for me, when I did my PhD in phytoremediation, which is a really cool thing because those plants can take up, you wouldn't think so, but like sunflower really good for, phytoremediation, plants cleaning up the environment. So I'm a real big proponent of that. That'd be a really cool kind of presentation. If that's something that y'all are interested in, we'll get some topics on that. We'll have those later on down the road. But it's those types of things that I think about when I think of biogeochemical processes. It's a plant and the environment, air plus the soil environment that is helping fix this soil problem. And that's the environmental aspect of it. I see you nodding your head too, like those are thought processes.
I worked on visited a place where they were doing some bioremediation. It was like an old mining, like did some strip mining in that area. They're cleaning that up.
Right.
State of Tennessee is.
And so bioremediation would be, if phyto is plant, bio is, I'm trying to have a discussion. Microbial. Right? It's just microbial remediation. Have y'all had any experience with that, or is that an interest, or don't know yet? Just, are we done yet, Natris? Hopefully we'll get to have more conversation as we start to move into these things and ideas start getting flowing. But so phytoremediation and bioremediation are going to be two of those things. Mining sites. EPA Superfund sites where they have this acid mine and draining. You can take this into just about anywhere. Y'all will see when we get into soil conservation. I think that's where we'll start to get the extra thought processes into, hey, you know what? We could really just reduce, if we change the pH, that would cause precipitation of this element to fall out of the solution. The river would get cleaner. Right? Does that make sense? Can y'all understand? Yeah, can you see it? That if we change one of the chemical properties of the system, we can cause a precipitation so that it falls out and the water continues on. No different than if we slow water, we can have the soil drop out, right? Because if we slow the flow, we have the time for soil to settle out. Same thing with chemicals. We can apply these principles of biogeochemical cycling to clean up rather than trying to remediate with some chemical. We're basically going to use the environment to clean itself up. And then finally, these plants are transforming these inorganic nutrients into organic nutrients. And so in the soil, the nutrients might be immobile. And that's organic or inorganic to organic. When the plants take it up, it's mineralized, and then they immobilize it in the plant. And you remember that from fertility. And I'm pretty sure I beat that into y'all's heads pretty good in soils. For some reason, people still did not know. Do you remember that? Mineralization and immobilization.
I have to refresh on it. It's been like 2 years, I think.
That's okay. I would rather have you tell me not a clue, Naturus, so that I can make sure that you do have a clue. Man, listen, this is practice. This is where we get to be wrong. This is where we get to say, you know what, I don't know. But when you get in front of the board members of whatever company or whatever you work with, and you go, I don't know, they're gonna go, we're gonna hire someone who does. So that's kind of my goal here, is to make sure that you do know before you get out, okay? Don't worry, I've got it in here, we're gonna go over it again, all right? And then so plants are gonna decompose, and those organic nutrients are gonna be mineralized back into inorganic nutrients. So plants decompose, all the nutrients that they have in their tissues are going to be used by the microbes. The microbes will transform it from inorganic to organic. I'm going to retry this. Can't wait to get my good markers. I'll give them to. I will. So nutrients in the plant are organic. So in the soil we have inorganic. Can you see that, Isaac? I want to move it over a little. I'll try and work from right to left. How about that? Poorly dead plant. Right? Immobilization, mineralization. Immobilization, it's in the soil as an organic nutrient. Converted into from inorganic to organic. Mineralization is converted from organic to inorganic that the plants can then take up. But once it gets inside the plant, they return it to organic. Because they're organic, right? When they die, those organic nutrients are then reconverted into inorganic nutrients. And that cycle just continues. Okay, I'm watching.
I was looking at that, yeah.
Again, I'm gonna go over it some more.
Okay.
But in soils, it was like, there was this problem. Some students got it, some students didn't. They couldn't understand it. Immobilization is inorganic to organic, and mineralization is organic to inorganic. I know. I'm watching Cassie.
I'm sorry.
You're okay. I learned from last semester to kind of give students the time to write the things down they need to, and I'm trying to set my PowerPoints up such that they kind of lend themselves to that. So now we're going to talk about where do we get these ions from. Again, we're going to think about this in the biogeochemical sense of things. Starting with the geo, mineral weathering. Different from mineralization. This is a rock that heats, freezes, wet stalls, something breaks off, erosion processes, water, wind, more minerals break off, mineral weathering. Organic matter decay. Plants have organic matter. Ants, deer, anything living, organic matter decay. Nowadays, rain is a source of ions, right? We have acid rain, nitrous oxides, methane, sulfur oxides, there's lead, arsenic. Some of those things are floating around in the environment, you know what I mean? And so they are attaching into the air that condenses, that has water in it, that takes on all the chemicals that are in the air and then drops it onto our soils. Irrigation waters, because now we're drawing from places that, let's say you draw from a lagoon, or you draw from a lake or a stream or a river or something. If you don't have enough infiltration to the ground, then that runs off into the stream, and all we're doing is basically pumping back onto, or pumping the nutrients from the irrigation back onto our soils. And so from a fertility aspect of it, it's a good thing to have your irrigation water tested, because you're going to get some nutrient supply from the irrigation water. A couple of examples of that. I had a friend who, a colleague that was saying that they were doing nitrogen experiments and they were applying the nitrogen, but they weren't getting a response. Turns out that the irrigation was loaded with nitrates. So they were adding irrigation and they were basically just wasting the, first off, the experiment was wasted because you couldn't test whether or not the nitrogen was causing the thing because you got no response. And then second, there was another instance where a material was being used, and this is from my PhD, the material that they were using had element in it. And then all the runoff was being sequestered in these retention ponds. And guess what they were using? And so this is like at a mine site, right? And so you know when it's dusty roads, you spray water over it. And guess where they were getting the water from? All the runoff. So guess what was in the water? Stuff that was in the road. And if you continue putting on, and so as the water evaporates, the concentration of that element becomes greater. When it rains, more of that element, and it's just this never-ending cycle. So understanding that it might be the irrigation water that's giving us this problem. Fertilization makes sense because our crops need more nutrients than might be what is supplied by the soil. Let's go back up one. And then the release of the ions from the mineral weather or the organic matter decay. So now we're going to start getting back to soil. You've heard the term soil colloid. That might be familiar. And so Annalisa asked me, what does it mean to be, what is a colloid? And it is this, I mean, well, she kind of stumped me, like I was just like, man, it's the soil colloid. But really what it is kind of like, have you worked with prodiamine? Barricade is yellow.
No.
Well, so any type of those chemicals are kind of like emulsifiable, and they'll be in suspension, right? And so that's kind of what a colloid is, like fog. It's one little piece of condensation, like this cloud kind of thing, but all together collectively they make. But you couldn't go pick out a piece of foam. Whereas I can go pick out a piece of soil. I can get, you can't pick it out. It's kind of like it's in suspension. It's really difficult. If you remember from soils, did you ever do like the Boyakos method where you shook the, no? Hydrometer? You have, right? It's the hydrometer method. And so basically you take 100 grams of soil, you put it in water, long story short, after about 2 days, not all of the soil falls out of the water.
Oh, we did that.
You did that?
Yeah.
With the hydrometer, and you put that in and you were able to read that?
Yeah.
And like at first the sand settles out really quick, right? And then next it takes a little while for the silt to settle out. But you can never get that clay to settle out because it's so light that it's in suspension. And you couldn't go in and pick out that piece of clay. Like that actually has to go through a super, super fine mesh filter in order to get that out, in order to be able to actually see that. It's almost like it's impermeable to get that out. Like you're talking like 250 mesh or greater. So that's kind of what we're talking about when we say like a colloid. Collectively, you can see it. Individually, you probably couldn't. They impart some adsorption or exchange of ions and gases and water. We know that the greater the clay content, the greater the water holding capacity, right? They got to be running some machine up there. Or maybe it's where the heater or the air conditioner is. Soil colloids are important for the soil chemical processes essential to life because it's the holding on to and the release of our nutrients. Surface property is dictated by type, whether it be how much plant material is there, and also what type of clay mineral it is, or whether it's a 1-to-1 clay mineral like kaolinite, or whether it's like a 2-to-1 clay mineral like smectite, montmorillonite. They go into this whole phyllosilicate, inososilicate. Like when I was making the PowerPoints and looking at the stuff they were talking about, it was like, I've never heard of an inososilicate. Never even been around it. Didn't even go over it when I took soil chemistry. We went over the big ones, kaolinite, smectite, maybe some micas, and your expanding clays. Like those are the things y'all are going to be the most exposed to when you get to your jobs. All right, next slide. And so the soil solution is going to be this kind of mix between the water that's there, some of those colloids that are there, some of the nutrients that are there, kind of just like in the atmosphere, right? That is actually a solution. There is some moisture, there are some elements, oxygen, things of that nature, and that is what we're terming kind of the soil solution. And so soil chemistry is about the exchange and the interface between the soil solution and the soil physical part, the solid phase, so the actual soil piece, and how water interacts with that piece. And so we remember from soils that the greater the surface area, the greater the attraction, and the more reactive sites that we have. So in clays, we're going to get the reactions that happen are going to happen more in clays than they would in sands, right? Like I know I'm not telling you anything you didn't already know, just kind of reinstilling that it's good to know what kind of soil you have. So it's good to take a soil test, send that to the lab, have them do the Boyakos method because that's boring. It takes forever. Sometimes it's expensive. You can do texture by feel and kind of go, you know, there's a lot of clay in this. There isn't a lot of clay. These are things that are going to help you understand the absorption processes for chemicals. And so when someone says, hey, you know what? I put down this pre-emerge in this clay soil, and you go, well, what kind of soil did you have? Clay. How come on the label it says that I have this much time before this chemical is no longer reactive? How come it's still reactive? I mean, you got clay soil. It's adsorbed to that. We start getting into pKa, environmental fates, things of that nature. And I think that's where soil chemistry is going to fit in the most for y'all, is understanding the environmental fate of these nutrients and chemicals and how that's going to work in sustainable agriculture or just environmental health, period. We just don't want to be polluting our environment. And this thing contains this diffuse double layer. So we're going to get through this garbage about getting into the intro of soil chemistry, and then we're going to talk about this diffuse double layer in that. I need a bigger board. That we have this positive cation that is attracted to that negative site, right? I know y'all remember this from soils. This is basic cation exchange. But that there's an extra double layer here where we start to get, where we can have this shift. It's kind of like standing in I guess before COVID, when you were at like a concert. You didn't always necessarily stay in your one spot, right? You would move a little bit, or someone would bump into you, or standing room only. And you're constantly moving, and these, like, you can't just stand still and just watch the show. There's always some movement going on. And so that's the same thing with our soil colloids. There's always some movement going on. And what they found was that there's this area that is basically dictating what movement and what cations are in the soil solution. Because remember, we're talking about this being the solid phase, and everything, and we're talking angstroms. Y'all know what an angstrom is? Super small, okay? Angstroms. In that soil solution. Like, if you can think about it from a theoretical standpoint, that there's this very, I guess I should do it right here. There's this very small space. There is still space between my finger and this wall. Because there's space between the cell of my skin and the very surface of this wall. I mean, you really got to stretch your imagination for that. But that's what they teach us in chemistry, right? There is going to be some airspace between, even though I'm pressed all the way against it as I can, there is some space between the very cell of my skin and the basis and the beginning of this wall. And that's the same thing right here with the soil solution. That there is some space right here. All right? I don't know how they did it. They had to use some electron microscopes and come up with this diffuse double layer theory because they can't really prove it, but it makes sense. We'll run with it. So that's this layer of water directly contacting those solids. There's a little layer of water around each one of those chemicals. And that is what that space is between my finger and the cells in my finger and touching that wall. good?
That rolls. Was not expecting that to put the brakes on.
All right, so I added these in here. I just kind of want to get y'all start thinking more chemically now, because as we move forward into this, I'm going to start using more chemical terms. We've got most of them up here, but we're going to start getting into those elemental compositions. Something that I wanted to notice is this hydrocarbon here. And then also methane, which is another hydrocarbon. So in methane, what is the, see where it's, how we have this CN and then H, 2 times N plus 2. That's really kind of how methane is written, right? You have 1 carbon, 4 hydrogens. So 2 times 1 is 2, plus 2 is 4. Okay. When I was looking at that, I was like, wait a minute, that's also a hydrocarbon as well. And many of these, also these nitrous oxides that we absorb from the atmosphere, were also given back off as nitrous oxides as part of denitrification. But just to understand that, like, these are some of the things that change. And when these concentrations change in the soil, we start to have some other change that's affected, like the slate clean, start over, right? So it's constantly dynamic interactions are changing. So Le Chatelier's principle is basically saying that when you add something to a system, a change will occur, and it's probably going to be in the opposite direction of when you added it. Kind of like a seesaw. It will move to either the left or the right. So if we have some heat if we add heat to an ice cube, we all know that it's not the heat that's melting the ice cube. The ice cube is actually taking on the heat and therefore creating water. Same principle. That is the Le Chatelier's principle. That if we add some chemical to a solution, that if we add salt to water, that the sodium and the chloride will separate. And then finally pressure. So when we have these changes and these releases of those, that interaction with the atmosphere, when we have a release of carbon dioxide or a release of water vapor, we change some pressure inside the soil. That is going to change some of this reaction. Each time one of those changes. And so most chemical reactions are thermodynamic, meaning heat, right? Where do we get our heat from? The sun, correct. So we get, I'm not gonna ask very difficult questions. So feel free to jump out there. We get it from the sun. And so the sun is never constant because we have clouds. So this is constantly changing. So whether we're adding this energy in the form of heat, this reaction is going back and forth. Sometimes it's huge. Sometimes the change is great. We have a problem. Other times that change is minute and it's not a big deal yet. And so that's why those thermodynamic reactions. So when I was doing my PhD and looking at the phytoremediation and all these things and thermodynamics, consider a big fish pond. right? Or just a big pond, period. And whenever something enters that pond, whether it be a raindrop, whether it be a stick, a bird, a fish moves, there are some waves that move, right? That changes each one of those reactions. That changes this because it's pressure or some heat or some chemical. We add a chemical to it, it changes a reaction somewhere in that system. And that's basically what Le Chatelier's principle is talking about. All right, last one. So this flow of energy, known as Gibbs free energy, is basically saying that when we add something to a system, whether it be heat or whether it be chemical or whether it be pressure, it changes. There is a change. And so, how many of y'all knew that delta meant change? There's going to be a delta somewhere. It has to, because this has to be in equilibrium somehow. This is going to change when one of these two changes. Right? Very simple system. Enthalpy. I guess the best way I could think about this is, to explain this is part of Newton's law that an object at rest remains at rest until acted upon by some outside force, right? There's a ball on the floor, it's not going to do anything until I add energy to it. Once that energy is added to it, that ball eventually will stop. If the ball would just roll, the amount of energy that I put in and how far that ball rolls is we start getting into friction and pressure and how much wind, if we add wind, whatever, doesn't matter. At some point that ball would not continue, unless we were in space, right? If you were to, in space, kick a ball, it would just continue on going because you have put it in motion. That's not the case on Earth. At some point, I wanted to bring a top. Anybody got a quarter? Anybody got any change? It's okay. I guess if you guys can think about it, that if we were to spin a quarter on the table, me spinning the quarter would be enthalpy. At some point in time, that quarter will fall, right? That is entropy. To go to a state of disorder. Because when it's on the floor, nothing's happening. Once it stops, just like a top spinning, eventually it will wobble. And so in an environment like a pond, that when some motion happens, eventually it will go too slow. They're always trying to get to a state of equilibrium where everything is just copacetic. And then finally, the biggest factor is temperature, because they're thermodynamically driven. And so, to go from water to ice, what happens to the molecules? Going all the way back to basic chemistry. Do they speed up or slow down?
Slow down.
They slow down and form a solid, right? So as temperature decreases, entropy will increase. Make sense? It's quicker. So if we were to have this reaction or whatever, this ice or water, if I were to spill water on the table right now, the temperature is fairly warm, it would take a long time for that to finally reach equilibrium. But boy, if we were to do that and it's really cold, I know y'all seen the thing where they throw the water out, it's like it's North Dakota, Canada, and Alaska, and they throw the water out and it freezes instantly. The energy of throwing the water out is the enthalpy, the heat of the system, because it's warm, right? Because it's not frozen. We're throwing that water out and it freezes in midair. So it went to entropy very quickly to ice. The molecules slowed down very quickly because of the temperature. And so because things are so thermodynamically driven in soil solution or in water or any of those things, temperature is going to play a big role in that. And that's kind of basically, this whole thing is about the free energy and kind of what they base a lot of the empirical methods on. Each time you change this temperature, you're changing the entropy. Each time you add a heat to a system, it never, after a semester, I looked at it and I went, it never stops. It never really does, because it's constantly moving. We're constantly changing temperatures. It's getting hot one day, it's cold the next. It snows one day, it's cold the next. So each one of those are going to change. So it's, I guess the takeaway message is that soil chemistry is dynamic. It is very rarely is it static. It will constantly be changing. Your best guess is just that. It's a best guess. And that's kind of disheartening. But guess what? No one else can make a guess at it. You will be the experts at that. So having the understanding and knowing how to portray that and say, in my professional expert opinion, I believe that spraying this chemical won't have this effect on the environment. Sound good? I promise I won't stand up here and talk all day. This is just the first one to kind of get back into it. I do want to have discussions and articles and other different things, and that'll come with time and getting comfortable. All right? I'll see you all in about an hour.